when you're dealing with an n-type material, and I say majority carriers, I mean electrons. And if you talk about majority, then we also talk about minority. So in n-type, if I say minority carriers, we'll talk about holes, right? If I talk about p-type material and I talk about majority carriers, that would mean holes, and minority carrier in that case would be electrons. Why are we introducing these terminology? Because when we treat the uh, dynamics of charge carriers in a device, then discussion would be independent of whether it's n-type or p-type. We'll just talk about majority carriers and minority carriers, because then you can apply that knowledge to n-type and p-type equally, right? So this is a slide where I see like 5 questions in exam I can make easily. That what is majority carrier in an n-type material? That's electron. What is majority carrier in n-type material? They're holes. What is same way if I look on the right side, what is the majority carriers in case if you dope it with acceptors? That would be holes. What would be minority carriers if you dope it with acceptors? That would be minority carrier. That would be electrons, right? Just some terminologies which are interconnected, and I hope you guys can remember those. Right? So far, so good. Now, there's one more thing, and then probably we'll wrap up. A simple thing. We have seen before that we can make different materials on top of each other, right? What we call a process called epitaxy, where you could make multi-layered compound semiconductors. Now, in that case, what would happen is instead of a continuum energy structure, which we could get from this equation, we would have different levels of valence band and electron band. So, for example, this material has these levels of conduction band and valence band, but if you chain it to gallium arsenide, that has a different band gap. So hence it has different conduction band and valence band, right? Now, if I again go back to that, then again the band gap becomes the larger one, right? So what if I dope just the center part? Then that would introduce these other levels just in that center part. Now, physically, this would be a, if you look at it, yeah, you can see one material finishes here, another material, but this is the same device. You have maybe it's an optical device where you are using photons, getting photons out of it. But what is the band energy that you will use? Will you use this one? Will you use this one? Will you use this extra one? What do you use? So it's an important question because it's look the same continuous crystal lattice but with different band gaps. So what we do is then we use the area which is active. So for example, if we are looking at photons coming out of just this region, then we would be using Eg with for that central part, which is 1.43 plus E1 and plus EH. So then we would be, that's the whole energy that a photon, that electron will have to jump, and accordingly the wavelength will come out from that whole energy from that part, right? So this is the concept of what you call as discrete quantum states. So there's a quantum states here, and then there are here and here, and then there are new ones introduced, which may be because of a material, which may be because of strain, but nevertheless, those extra energy levels have to be accounted for if you're talking about just BART, right? And the reason is that, remember, if we had discussion for quantum levels and quantum confinement, where a particle was confined between two big energy potentials, that's the same thing happening here. This energy level is much higher than the center one, so particles are confined to this part and they cannot get past the two high levels on both sides. If you think about it, the both in Valence band also, these are at high levels. On the uh, conduction band also, these are high levels, so they cannot jump and come out. Instead of that, it's easy for them to just this part and go out if they are optical materials, right? So, which means that if you have this kind of material, the only place where you can get photon outs would be the small part with smaller energy band gap. That makes sense? This is a concept what you call as quantum confinement, right? So, and this is the same thing given in English, that electron can make a transition in a quantum well, giving off a photon of energy greater than the actual band gap, right? So